In this video, we're going to show the basic idea of how to reparameterize a vector function in terms of its arc length. So let's recall that if we have a path C that is traced out by some vector function, and that vector function has a derivative that's continuous along that path, and that it traverses the path exactly once as t increases from A to B. So these are some standard initial conditions that make our vector function, let's call it a well-behaved function, nothing strange is happening in there. Then we should be able to reparameterize it in terms of its arc length. So we'll start by using this arc length formula here and also consider a little concept drawing to make sure we understand what's happening. So if a vector function traces out this path C, we'll begin this length of arc at a designated parameter value. In other words, we're going to let alpha be the parameter value that begins the arc, and we'll hold this value of alpha constant. So our initial vector that begins the arc is the vector function evaluated at alpha. And then we'll sweep out a section of arc that terminates at this other ordered pair that is the terminal point of another vector, but let's let the value of the parameter of this vector be a varying quantity, t. Now we have used the value L to represent the length of arc, but in this particular case, let's consider that this length of arc is something that depends on the value of t. As the value of t changes, this vector would be sweeping either not quite as far or perhaps even farther. And as this vector sweeps in this direction, that's going to have an impact on the length of arc that is traced out. But if the vector is in a different position this way, then I'm also going to have a section of arc that is then longer. So the section of arc that is traced out depends on the value of t. And if t is a varying quantity, then this arc length also depends on t, that variable. So instead of using L to represent arc length, we'll use the alternate variable that is commonly used for arc length or position, which is s. Let's say s is the length of arc depending on the value of the parameter. That arc length is going to be traced out starting from the constant value alpha, right? The alpha that begins the interval was being held constant, and the variable t is the upper limit or the value that's going to determine the end ordered pair of the arc. The integrand is still going to be r prime. Now we had r prime of t up here, but that was when we had constant limits of integration. If we're going to let t be the variable that is one of the limits of integration, we need to change this variable to something different. So we're just arbitrarily going to call that u and then close mag bars, and then we are integrating with respect to u. And actually this is r prime u inside here. So when we calculate this antiderivative, and whatever we end up with here, we're going to be plugging in the limits of integration. This lower limit is going to be a constant value. This upper limit is going to be a varying quantity. And once we plug all this stuff in, what we'll get is a variable expression in terms of t. So we're trying to be super general here in order to describe this process. I'm just going to say the arc length turns out to be some variable expression in terms of t. Now if I have some variable expression in terms of t that is the value of the arc length, we could solve it for t and end up with t is equal to s minus 3, or that t is now equal to some function of s. So jumping back into the general case here, we could solve this for t to represent that parameter as a function of the arc length. Now let's recall back here at the beginning that this path was traced out by the vector function r at t, and r at t right now depends on the parameter. But since we can express that parameter as a function of s, what we can do is take that vector function, substitute all the t values with this function of the parameter, and ultimately what this thing then becomes is a vector function that has the arc length as the independent variable. So essentially what we're doing is we're letting the parameter be the upper limit of the integrand, the lower limit is some constant value. We're integrating in order to get a variable expression that is in terms of t, and then solving that for t in terms of s, and then using this as a substitution for t to get the original vector function to now depend on the arc length.